Hello everybody. So this is day 13. We're talking about continuous random variables. This is going to be a little bit longer and it's supposed to serve us for 2 days. So you're not going to see a day 14 video. All right, so where are we in all of this? Well, we've talked about basic probability and the two basic rules in random variables, which is an extremely important concept in inferential statistics. We looked at two examples of discrete random variables, and that's binomial and Poisson. And today we're going to talk about continuous random variables, namely the uniform and normal distribution. Day 14 is not going to be a video. Day 15, we're going to have a video on the sample means and central limit theorem. Day 16 will be point estimates and confidence intervals. And then following that, we're going to begin to prepare for the celebration of knowledge on day 18. The goals for the lesson is to understand this very important concept. Area is probability. So that's the way that continuous random variables works. The area under the density curve represents the probability. That's how you compute probabilities with these. The two distributions we'll be looking at is the uniform and the normal. For the uniform, we want to understand the requirements, when to use it, its PDF and parameters, and how to compute probabilities with it. That will mainly be geometric. We'll use geometry because the probability distributions are all rectangular. For the normal distribution, we will talk about when it can be used fairly loosely. It's a fairly robust model, can be used in a lot of different places. And then we will talk about its probability density function parameters and how to compute probabilities with it, which is very, very important. And it cannot be done with a pencil and paper. It'll need to be done using Excel, and I'll explain how that is to be done. Okay. As far as motivating examples goes, many quantities can be modeled using a normal distribution, such as reaction time, height, weight, IQ, etc., etc. Recall that for continuous random variables, you have a random variable, and for x to be continuous, the set of all outcomes, which we denote as Sx, must be a continuous set, and so that means it has continuous data. The probability density function has to be greater than or equal to 0. And the integral of the probability density function, which is the area underneath the curve, has to equal 1. It's the area that's the probability, so it makes sense that the area under the whole curve, all of the possibilities, that area comes to 1. Do not worry about the calculus part. We're not going to do calculus. Okay, let's take a look at that now. If x is a continuous random variable, the probability that x will be between some value a and b, those are on the x-axis, is the area under the probability density function. This area is the probability that x will be from a to b. So the first continuous random variable that we will be looking at is called the uniform distribution. So this is when you have a situation in which there's a lowest possible value and a highest possible value, and all values between are equally likely. Its probability function is a rectangle. If a is 1 and b is 3, in this example, then the probability of something occurring that's less than 1 will be 0. The probability of something between 1 and 3 occurring is going to have some probability, and that probability is contrived. So the total area here is 1. The area of a rectangle is base times height. The base, the difference between B and A, let's call this the width, W. So width times height gives the area. If the area is going to be 1, and I know the width to be B minus A, which is the distance between A and B, then if I solve for H needs to equal 1 over B minus A. And that's exactly what is reported here in the probability density function. If x is less than a, then the probability density will be 0 because there's no chance of it occurring in that region. If x is in between a and b, then the probability will be a constant 1 over b minus a. And if x is bigger than b, the probability is 0 again. Okay, let's look at an example. At a DMV, waiting times can be modeled by a uniform random variable in which the maximum wait time is 25 minutes. We see that there on this plot. And the minimum wait time is 5 minutes. Okay, so perhaps somehow the DMV has these measures in place to make sure that waiting time is uniformly distributed between 25 and 5 minutes. So it might be that if the line gets so long, employees are diverted from whatever it is they're normally doing to help with processing customers. When it gets down to a particular line length, they reallocate the employees to different areas, and that sort of slows the speed. Maybe with measures like that, they can get the density uniform. The data, like our dice example, is not exactly uniform, but suggests a uniform distribution. Okay, so if it is a uniform distribution with values appearing from 5 and 25, then the probability density function here is going to be 0 when x is less than 5, 1 over 25 minus 5, which is 1 over 20. I want the area to be 1, so 1 equals width times height. The width is 25 minus 5. So h needs to equal 1 over 20. That's the density when x is greater than or equal to 5 and less than or equal to 25. If x exceeds 25 in any way, it's going to be 0. So that is the probability density function of my random variable. Now, the question is, what is the probability of waiting for 10 minutes? I'm going to make a change here, say of 10 minutes or less. The probability of waiting for exactly 10 minutes is 0, but for 10 minutes or less, we're going to figure that one out. Okay, so remember that the probability is the area under our density curve. And so we are looking for the probability that x is less than 10. Here's 5 to 25. Here's 1/20th. And I'm going all the way to 10 here. So I need to find the area from 5 to 10. The width is 5, and the height is 1/20th. So this area is going to be equal to 1/20th times 5, which equals 1/4. So the probability of the waiting time being 10 minutes or less is going to be 1/4. So that's the uniform distribution. And now we're going to go on to the normal distribution. A famous statistician said, "All models are wrong, but some are useful. Rarely do you find a situation that exactly models the normal distribution, but some are very close. And generally, the normal distribution works at predicting things very, very well. And so we use it and study it. Basically, you can use the normal distribution if, and here are some sort of soft requirements. The data is quantitative continuous, symmetric about the mean, and bell shape. And so if it has that shape, you probably won't go too wrong by assuming a normal distribution. Now, the data does not, strictly speaking, need to be continuous. If it's discrete with a very large number of possibilities, well, you could also use the normal distribution to model that. These are guidelines. The question is, how well does it work? Let's look at the mathematical description of the normal distribution. The normal distribution has two parameters. The uniform distribution had parameters A and B, and those are arguments that you put in that define the distribution. The normal distribution also has two arguments that define its distribution, and that is the parameter mu, the expected value of x, and sigma, the standard deviation of x. And you give it those values, and what you get is a distribution that has mu as the expected value and sigma as the standard deviation. This is the formula for the probability density function. It's very difficult to integrate. In fact, it's impossible to integrate. Even if you had calculus, you could not compute the values that we're going to need to determine in this lesson. You couldn't do it. It's that complex of a function mathematically. And so what you would end up doing, and what we're going to be doing, is using Excel to compute the probabilities, to compute the areas under this very interesting curve. Excel has a function called norm.dist, and that function has four arguments. Let's go through them. First is the x value. That's the value that you're interested in. The second is the parameter mu that defines the distribution, and the third is the parameter sigma that defines the distribution. The fourth argument is a binary input that's either going to be a 0 or a 1. Now, when you open the function up in Excel, it'll say cumulative for that argument. If you plug in a 0 for that argument, then what you're saying is do not take the cumulated probability, just take the probability right at x. And what that gives you is not a probability. It gives you a relative frequency or probability density. If cumulative is 0, we hardly ever use cumulative equals 0. On the other hand, if we stipulate cumulative equals 1, then that means basically true here. We do want to get the accumulated probability up to the point x. Then that is going to give us the left-hand area from negative infinity to x. Excel gives you the area from the left to x. Not from the right to x. You would have to take 1 and subtract the area from the left. So this is what Excel gives you. Excel does not give you this. You have to find the area from the right by subtracting 1 from the area from the left. Because remember, the whole thing has the area of 1. Okay, more about that sort of a thing here. So Excel only gives you area from the left. To find the area between 2 points, well, we're going to have to get a little creative. So the normal distribution using Excel, again, suppose that x is normally distributed between mu and sigma. So those are two given parameters, a mu, an average, and a standard deviation. If you want to find the probability that x is between A and B, well, you have to do it in 3 steps. First, find the probability of x being less than B. Then what you do is you find the probability that x is less than A. And you do that from the left, so that area from the left. If you subtract the area to the left of A from the area to the left of B, you get what you're looking for. You get this area right here. So you're taking away this area here from this bit. And what you get is what remains right there. And so these lines right here is what you put into, these pieces right here is what you put in Excel. Here's an example of the normal distribution. The top of a certain door on a submarine is 175 centimeters from the floor. Using the normal distribution model, we've got data to estimate the mean for our population, for our populations, the mean and standard deviations of our populations. So we're going to use as the mean of the males 4 centimeters and the sigma for the males 7.59 centimeters. Using the normal distribution as a model, what is the probability that a woman would need to duck to go through the door? What is that probability for a man? First, we need to find our parameters, the things that we plug into our probability density function, our probability distribution. So we've got the average for males and the average for females, the standard deviation for males and the standard deviation for females. I'm going to have X be the height of a randomly selected female, and Y will be the height of a randomly selected male. And so this first question here, what is the probability that a female would need to duck going through the door? That is the probability that X, which is the height of the randomly selected female, is strictly bigger than 175 centimeters. Now I want to see what proportion of females is going to be greater than that. So I'm looking for this area which is to the right of that value. Now Excel doesn't give probabilities to the right, so I need to find the probability to the left and subtract from 1. That's 1 minus the probability that X is less than 175. This value can be computed in Excel using norm.dis 175, that's my X, that's the little x, and then I plug in mu for the females, sigma for the females, and then my cumulative entry is going to be 1 because I want the total area from the left. I want the area. Let me hop over to Excel. Here's a blank sheet I filled in. I filled in the mean and standard deviation for the female data. Now I want to find the probability of X being greater than 175, and I reasoned that that was the same thing as 1 minus the probability of X being less than or equal to 175, which is what Excel is able to give me. Now the probability that X will be less than 175 is equal to norm dist. X is 175. The mean is going to be that mean right there. The standard deviation will be that standard deviation, and the cumulative will be 1. Press enter, and there's my probability there. Now that's not what I'm looking for. I want 1 minus that. So I'll press enter, and that right there is the actual probability I'm looking for, 0.073. It's rounded to 3 decimal places. 0.0725, but let's round it to 0.073, rounded to 2 decimal places. So all of that equals 0.073, and that's the probability a woman will be taller than 175 centimeters and need to duck. It's not very likely. What's the probability a male will need to duck? We're going to use the random variable y, which corresponds to the heights of men. So we want to know what is this probability. That's going to equal 1 minus the probability that y will be less than 175, which is something that Excel will give me. Let me jump over to Excel. I've just put in my data, a mean of 178.4 centimeters and a standard deviation of 7.59 centimeters. And now I'm going to find those probabilities. So the probability that y, my male heights, is going to be bigger than 175 is going to equal the probability of 1 minus the probability of y being less than or equal to 175. So I do the same thing. I say equals norm dot dis, find it in the drop-down menu. X is 175, mean 178.4, standard deviation 7.59. Cumulative is, of course, going to be 1. So press enter, and there's the probability of y being less than 175. The probability of y being greater than 175 is going to equal 1 minus the result of the previous calculation. And so that gives me 0.63. Let's round to 3 decimal places. So that equals 0.673. And so that's the probability a man will need to duck when going through that threshold. Okay, now what I would like to talk about are percentiles. So when x is normally distributed with mu and sigma, norm.dis for x gives the probability of x being less than x. That gives me the probability, which is this proportion. Well, that proportion is pretty much a percentile, except it's not multiplied by 100. A percentile is a percent between 1 and 100. So if I wanted to find the percentile rank, I would take that value here and I would multiply it by 100. And that would give me the proportion of the percent of people in that population less than x. To find the x value, use norm.inv inverse. Norm.dist takes x and gives a p. For the inverse, put in the proportion of the population that is to be less than x, and I want it to give me out that x. I'm going to use the inverse function. I'm going to put in that proportion, and it'll give me out an x. Okay, let's take an example. All right, so normal distribution example. In industrial design, it is common to try to accommodate 95% of the population. This means making doors tall enough to accommodate a 95 percentile man, while designing door handles, say, for a 5 percentile female. Here are our parameters from the data. Here's the statistics from the data that we use to estimate our population parameters. Using the normal distribution as a model, determine P5 for females and P95 for males. So what I want to do is I want to find the X value among females that makes this area 5%. What is that X value? In order to do that, we're going to use norm.inv. So I'm going to use norm.inv, and I'm going to put in the p-value that I want. Now it's looking for a probability, and that probability here is 5%. So we want from negative infinity to some x to be 5%. So that's 0.05. That's my p. Comma, because this is for the females, we're going to have 164.7 as the mean, 7.07 as the standard deviation. There is no cumulative argument in norm.inv. So that's just going to give me my answer. Now for the y, I'm looking for a particular y value that's going to make this area less than 95% of the population. I want to find whatever y value is going to make this area 0.95. And so since that's the area I want to investigate, I'm going to go ahead and use norm dot for 0.95. Since this is for males, 84, comma 7.59. Now I go to Excel and type those in. Looking for P5, and that is going to equal norm dot inv. There it is. Probability in this case is going to be 0.05 because I want that percent of the total less than this value that it's going to give me. And so the mean here, I'm working with the females again. The standard deviation is going to be that one. Enter. 100.07 centimeters. So the original data here must be to the nearest decimal because the mean is to the nearest tenth. So I'm going to want to return my percentile to the nearest tenth. And so I'm going to report 153.1 centimeters. That's going to equal P5. Now let's just check and make sure that makes sense. It looks about where I drew it there. So this should be about 5% of the total female population. For the males, norm.inv probability is 0.95. The mean is that, and the standard deviation is sigma. Enter, and I get 190.9 centimeters if I round to the nearest tenth. All right. So there's the heights that we need to consider. We need to make the door handles high enough to accommodate somebody of height 153.1 centimeters, and we want to make the threshold high enough for somebody that's 190.9 centimeters. Now, given the actual data that I had, which was, I think the N was 2,000. I think I had 2,000 male and female heights. And among that, the fifth percentile was 153.1 for the female, so that's exactly the same as what our model produced. So it was a good model because it agreed with the actual data, but it didn't agree so well with the male data used. 2,000 measured heights was 191.1, whereas my stochastic model for the heights, I should expect a 95th percentile of 190.9. All right, so you win some, you lose some. The area under the curve gives the probability that x will be between A and B. That's true for the uniform distribution, the normal distribution. This right here is an F distribution. This one here is a Frechet distribution, which we're not going to learn about the Frechet distribution, but we will learn a little bit about the F distribution at the end of the semester when we're talking about ANOVA tests. It's always the same story. It's the area underneath the density curve that gives you the probability. Now let's talk about our parameters here. Let's start with normal distribution because that's easier. So as promised, if you take this probability distribution and you compute its mean, this mean here that you compute is exactly the same as the mean that you plugged into the normal distribution. The same is true with the standard deviation. You compute the standard deviation of your random variable and they match. And so, not surprisingly, so does the variance. So those are all what we would hope from the normal distribution. Now, from the uniform distribution, this makes sense because if you have a max of B and a minimum of A, on average, you might expect just to get halfway in between the two, which is what this is. It requires a bit of calculus to compute variance and the standard deviation, and so I won't say anything about that. These here are formulas, should be known about, not necessarily memorized, but you should know where to find them. Something asking about the standard deviation of a uniform distribution is not unlikely to be on the celebration of knowledge. Now, these things are significant because they help us to answer questions about significance. So, there's two ways of describing significance. One is the range rule of thumb. The range rule of thumb says a value is significantly high if it is greater than the mean plus 2 standard deviations. The value is significantly low if it is less than mu minus 2 sigma, so 2 standard deviations below. Now that's the range rule of thumb. Another way you can think about significance is that the likelihood of finding something that is as high or higher is less than 5%. If that's the case, then we're also going to refer to that as significantly high. A value x of a random variable is significantly high if the probability of getting a value that is as high or higher is less than 0.05. And so that means that's this right here. The probability that x is bigger than or equal to little x, that value whose significance we're curious about, if that probability is less than 0.5. So if finding something higher than it is a rare event. Likewise, a value x of a random variable capital X is significantly low if the probability of getting a value that low or lower is less than 0.05. Okay, now I would just like to mention the empirical rule, also known as the 68, 95, 99.7 rule. What it says is that if x is a random variable that's normally distributed with mu and sigma as its parameters, then 68% of all of the values of x, see, so x has a bunch of values in it that appear at a particular distribution frequency of that long list of values, 68% is going to be within one standard deviation from the mean. So that means it's going to be bigger than mu minus sigma and less than mu plus sigma. And that'll be 68% of the population. 95% will be between two standard deviations of the mean. That accounts for 95% of the data. Then 99.7% is between 3 standard deviations of the mean. It is difficult to see, but the shaded area ends and the distribution continues. Okay, now here's another percentile example. As part of a study, Denver Honeycutt took an IQ test with the UVA Department of Psychology, scoring 112. Now, IQ tests are designed to have a mean of 100 and a standard deviation of 15. What percentile is Mr. Honeycutt? I need to find the percentile rank of this data. I'm looking for a percentage out. I want to know what percent is less than Mr. Honeycutt's score. What helps me is to sketch a normal curve here because this is normally distributed. I've got 100 here, which is the mean, and then I've got 112. And I want to know what percentage is less than or equal to that. To find that, use the normal distribution. So I'll use norm dist, put in 112, that's the x, put in the mean, put in the standard deviation, and I want cumulative. I see what I get out. So Denver Honeycutt, what percentile is he in? Well, this is going to be equals norm dot dist 112 times the mean, and the mean is 100. Standard deviation is 15. The cumulative is 0. And the cumulative should be 1. I made a mistake. I looked at that thing and I thought, that is really quite low. And there was a bit of a pause there, which I think got removed when I edited this. But I thought, now that's very low, because I would expect his percentile to be above 50%, because he was above the mean. And so I looked at that. I Gave it the sniff test. I saw something smells funny here. So I'm going to change this now to 1 as it should be. Area, not just the height. Cumulative is true. I press enter, and there I go, 78.8%. And so that percentile will be the 79th percentile. Denver is in the 79th percentile. Okay, now Denver was hoping to be in the 90th percentile. What score would he have had to get for that to be true? So for this, I'm going to do norm.inv. I want to find what x value will give me an area to the left of 0.9. That's the 90th percentile. So 0.9 times the mean and standard deviation, and there's no cumulative parameter here. 119.2. So, and that sounds reasonable. It's a little more than what he got. He would have had to have gotten a 119.2, or 120 if you wanted to be in that percentile. Okay, now, as for a recap here, we looked at 2 distributions. We looked at how to compute the probabilities. For the normal distribution, we use the Excel function norm., and for the uniform distributions, we can do that by hand. We talked about how to compute percentiles. For the normal distribution, we use norm.dis to give us the percentile rank, because that would output a proportion, and the norm.inv for the percentile value from the data. Computing percentiles is fairly uncommon to do with the uniform distribution, but I think the distribution itself is simple enough that we'll be able to figure it out. We talked about when the model applies. Normal distribution applies. The histogram of the data is bell-shaped, and the uniform applies where the histogram is flat over a particular region, indicating a bit of a uniform likelihood. We also talked about the parameters for both of these probability distributions. We also talked about the empirical rule for the normal distribution and the probability approach to significance. That will be a very common thing to look at in the future. It's going to play a big role in hypothesis testing, and so it will be a recurring theme. All right, everybody, and then just one last time, I just want to say that the area under the density curve corresponds to the probability of the random variable being between 2 points. I want to drive that point home. Everybody have an excellent day, and we'll see you later.